Good morning, everyone. So we had the this off here. Hold on. All right. So we had the midterm. Midterm grades are out. If you haven't seen those, they're posted on Autolab. And let's just get right into this. Polymorphism. So this is the second to last lecture. We have this lecture, and then next Tuesday we're talking graphs. And that's it for me. I only have 2 more lectures and then the final exam. So the midterm, I think it went pretty well overall. There's a decent number of you who will have to take the final still, but an even larger number, like the majority of students, the majority of you don't even have to take the final. So that must be a huge relief for you. It's always a relief for me when students do well on something too. So I'm happy to see that. And let's get into polymorphism. And we're definitely in the home stretch. So for most of you, you got to finish up the 8 tasks. And once you do, it's over. 116 is over for you. You're done with it. So let's do polymorphism and get you ready for task 7. So task 7, we're creating this media library method. Class, we're going to use the 3 methods, the 3 static methods that you wrote from task 6 to populate a media library with movies and songs. We want one library with movies and songs, and then get the top K songs or movies from that media library based on some comparator that you're giving it. Based on Bayesian average rating. I hard coded this so we don't have to mess with comparators again. I already hate with comparators twice. So this is what we want to do. Fairly short description, but it's fairly compact. Each task is a little bit harder than has been in the past. So let's do some polymorphism to learn how to do that, because we're going to need one data structure that contains 2 different types of objects. How the hell are we going to do that? That's what we want to talk about today. That's what we want to build up to. So we're going to do that with polymorphism. So let's talk about what this is. This is something that was teased already earlier, very briefly earlier in the semester when we had the BST, and its constructor takes a comparator of some type parameter t, and we gave it a comparator, we gave it an decreasing comparator. And those types weren't the same. And I said, is this assignment even legal? How can we take a variable of type comparator of t and assign it a value of type int decreasing? It doesn't make sense. It goes against what we've been talking about since day 1. So that is actually allowed because of something called polymorphism. Now we get to dive into exactly what polymorphism is. Ooh, and I gotta drink this tea while we do this. Alright, so with inheritance, we had this game item class. Oh, why am I all... Alright, my hair's not that gray. I gotta adjust something here. Too tired to figure this out right now. No, I'm not. I got this. Good enough. Not great, but I ain't messing with it right now anymore. Okay. So with inheritance, and I'm covering up a little bit of the code. With inheritance, we had the game item class, and then we had weapon and health potion extend game items, so they inherited all the state and behavior from the game item class. And then we could override some of the methods that we inherited. So weapon inherited this use method, and then overrode the use method and said, no, use this one instead. And related to the midterm on Tuesday, this is one of the two major things I was looking for on the OP quizzes is uh, is when a method is called, do you call the right method? So we had the I just stared at them for so much time after the exam. The enchant and total weight. The enchant and total weight methods for OP, the quiz 1 or quiz 2, is do you call the correct one? One of them was overridden, one of them was inherited from the superclass. Did you call the right method? That was the big thing, and that's what we were doing on the midterm, and that's what we have here. Health potion doesn't override use, so it just gets the inherited use method. And then weapon overrode the use method that was inherited, so it's this method that's called from an object of type weapon. So anyone who got that wrong, called the wrong method at any time, they got to show up to the final. The other one was super constructor calls. There were, I told you in lecture, how many times I said don't forget your super constructor calls and how much we did that. There were a good number of students, I want to say 5, which is 10% of the class almost, didn't have their super constructor calls. Like, that was the one I talked about the most. Like, the only thing you have to do is not forget it, and to forget it, you literally have to skip a line in the trace. There were actually about 5 students who didn't have their super instructor calls. It's a big portion of the class. It surprises me every time. But anyway, that was inheritance. So with inheritance, we actually have this chain of inheritance. So the weapon class is extending game item, so we can visualize this a little bit. Weapon is getting all the state and behavior from game item. Game item doesn't explicitly extend any class, so game item extends the object class. So game item gets all the state and behavior of the object class, which means weapon indirectly gets all the state and behavior of the object class. So weapon has all the state and behavior of the weapon class, the game item class, and the object class. So weapon has all the state and behavior of 3 different classes. And when we have this extends or inherits from this relationship, we call this an is-a relationship. Because a weapon is a weapon, that one's obvious. But a weapon also, in a very real sense, is a game item. If it extends all of the state and behavior of a game item, it has everything that a game item has, a weapon is a game item, and a weapon is an object. This is very similar to geometry, how every square is a rectangle, every rectangle is a quadrilateral, every quadrilateral is a shape. It's that same thing, because a rectangle, a square has all the properties of a rectangle plus some extra properties. So a weapon has all of the properties, all the state and behavior of a game item plus some extra state and behavior. But it does have everything a game item has. And this brings us to what polymorphism really is. It's if an object is a type, it can be stored in variables of that type. And this is how we got away with int decreasing being stored in a variable of type comparator of t, where in that case t was integer, because int decreasing extends comparator of integer. So it is a comparator of integer. It can be stored in variables of that type. And that's polymorphism. You now know polymorphism. So that's it. Lecture's over. We can wrap it up. Like that. We have a few topics in the course that are just very simple to describe, and then it takes us hours to go into what that actually means for us. It was the same thing with binary trees. It's like a linked list with 2 references. Okay, that's it. And then we got to spend a while talking about what that means. So we do have a lot to talk about what all the implications of this are and certain nuances about this. But this is polymorphism. If somebody's thinking they're talking about polymorphism and they're not talking about this, then they're not talking about polymorphism. And specifically, it's polymorphism when you take advantage of this fact. So once you take an object of one type and store it in a variable of one of its supertypes, that's when you're using polymorphism. If you're not doing that, you're not using polymorphism. That's more important in the fall and spring semesters. We have interviews, so I go on this big long explanation, like when you're in your interview and you get asked, what's the difference between variables? Period. Everything else is inheritance. So since a weapon is 3 different types, it can be stored in variables of all 3 different types. We can store weapon in variables of type weapon, variables of type game item, and variables of type object. And here's the obligatory polymorphism definition slide. Polymorphism, poly means many, morph means forms, polymorphism means many forms. Our objects take on many forms. Our weapon has 3 different forms, has many forms. So all 3 of these assignments are legal. This code compiles, it runs, everything's perfectly fine with this code right here. We can create a weapon and store it in a variable type weapon. Great, we've done that all semester since day 1. But we can also create a weapon and store it in a variable of type game item. And this is a legal assignment. We can do this. It breaks one of the things I've been saying right from day 1 when I say a variable of type double can only ever store a double. If you try to put a string in there, everything blows up and it doesn't work. So polymorphism gets to bend that strong typing just a little bit, is if you have a variable of one of that object's super types, the assignment is legal. So we can store weapon in object variables of type weapon, game item, and object. These are all valid assignments. This is all completely legit. Oh man, my slides, I'm going into the bottom right corner a lot on these slides. It says weapon. And that's it. So when we have an object of one type, we can store it in variables of any of its super types. And once we do that, we're using polymorphism. Okay. So big deal. You would just create variables of type weapon anyway. So how does this actually help us? And what are the implications of this? What does this do for us? Like, I have a weapon in a variable type game item. Who the hell cares, right? So let's talk about what this means. I'm actually going to start with the downside. First of all, I think polymorphism is extremely powerful. I think polymorphism is the biggest reason to use inheritance at all. Inheritance alone is cool, and I had my selling points for inheritance. It lets you cut down the duplicate code, so you can share code among other classes, which is a very strong selling point in its own right. But the biggest selling point for inheritance is that it allows us to use polymorphism. This is the biggest thing. But I'm actually, I think it's so strong, I'm not even going to sell it yet. I'm going to start with a downside, because there's one big downside to polymorphism. So let's talk about that. When you have a variable of a certain type, you can only ever access the state and behavior belonging to the variable type. So when I store my weapon into these variables of type weapon, game item, object, and I want to call the get damage method. Get damage, if you recall, is a method that we defined in the weapon class. It was not inherited from game item. So game item does not have a get damage method, and object certainly doesn't have a get damage method. Object has toString, equals, hash code, and a couple others. Definitely no get damage method. That'd be weird to give every object in Java a get damage method. So from the variable type of variable weapon 1 of type weapon, I can call get damage all day. That's fine. We would expect that from everything we've seen all semester. We can make this call. But if I uncomment out this either of these next 2 lines from weapon 2 of type game item, I can't call get damage. Even though this game item variable weapon 2 stores a reference to a weapon object which does in fact have a get damage method that's ready to be called, it's ready to be used, I can no longer access it because I stored my weapon in a variable type game item, and game item does not know about the get damage method. Therefore, can't do it. Can't call this. Same with object. Object doesn't know about get damage, so I can't make this call. So this is a pretty big restriction that we have with polymorphism, is what we're allowed to call depends on the type of the variable. And if I want to call something like the use method was defined in the game item class, and then weapon inherited that use method. So I can call use from either weapon 1 or weapon 2 because both of those classes know about the use method. So I can call the use method from either one of these variables of these types, but I still can't call use from weapon 3 of type object because object doesn't know about this use method that takes a reference to a player. Can't call it. Doesn't compile. So what we're allowed to access is determined by the type of the variable. We'll get this T down. But what method is actually called, nothing changes with this. What method is actually called depends still on the type of the type of the object on the heap. So this variable type game item refers to a weapon, and if weapon overrides the use method and I call the use method through weapon 2, I still do get the overridden use method from the weapon class. So what method is allowed to be called depends on the type of the variable. What method is actually called works exactly the way it always has been. It depends on the type of the object. And we'll see this more clearly in the memory diagrams, and it's why I've always done the memory diagrams right from our first class, our first object that was on the heap. I always did this the same way, just so there's nothing to unlearn and relearn when we talk about polymorphism. I always go to the object on the heap, check the object's type, and then use that to determine which method is going to be called. That works exactly the same. In fact, we don't even put variable types in our memory diagrams, so there is no temptation to look for the variable type to find that method. There should be no reason to ever do that. We don't care about variable types when we're doing our traces. It's always going to the class matching the object type. For those of you who will be taking the final, I won't put this on the final exam. During the fall and spring semesters, we always have polymorphism on a quiz somewhere. It just doesn't fit in the way some are structured. It just doesn't go anywhere. So I won't throw this at you on the final. The final will look just like the midterm, just with different quizzes, but it'll be the same exact learning objectives being assessed. Man, I can't get that sentence out. I need more tea. The final will look just like the midterm. It'll be new versions of each question, but each question will assess the same things that were being assessed on the midterm on Tuesday. So I'm not going to throw this at you on the final exam. It wouldn't be fair to anyone who has to take the final. You couldn't get on the midterm. You need the final as that last chance to pass the class. I'm not going to throw new stuff at you and make it even harder. Like, that'd be very unfair. So I'm not going to throw that at you. But that's in the fall and spring. That is a big deal. Making sure that you're going off of the object type for what's being called. All right, and toString, this is a method that's defined in the object class, so we can call toString from anywhere. We could even call toString from type parameters. The variable type just doesn't matter. If we want to call toString, we're always calling toString. And all three of these calls, no matter what, they're being called through variables, through objects of type weapon. That means we will get the same method called every time, no matter what it is, no matter what we did in the overrides in both game item and weapon, whatever's going on there, we will get the same exact method called all three times, no matter what. Because the method that's called depends on the type of the object on the heap. Okay, so why would we ever do this? I'm glad you asked. Good question. Why would we ever do this? Which clearly we're just restricting ourselves, and we haven't gained anything. I haven't talked about the benefits of polymorphism yet. That's what we're about to do. But you would never actually do this. You would never say game item weapon 2 equals new weapon. You would always say weapon 1 equals new weapon, because you can, and there's no reason not to. You would always use this first line, this weapon one line. You would never just store your weapon in a variable type object. I was just using that as an example of how polymorphism behaves, but you would never actually do that. Where you will do this, where you will store objects of one type and variables of another type, is when the assignment is across a method call, when it's across stack frames. That's where this really becomes useful. So we want to simplify other classes. In the player class, I want this use item method. So if we don't have this use item method, I have weapons and health potions, and I'm going to need two separate methods for them. I'm going to have my player class that has a public void use health potion method that takes a health potion, and public void use weapon that takes a weapon. I need a separate method. If I'm not embracing polymorphism, I need a separate method for every single type in my game, which is kind of annoying with two types. But what happens when we have 100 different types? And every time I add a new type to my game, I have to go to my player class and add a new method to use it. And that's going to get extremely tedious. That's going to get painful to add new items. It's going to be to the point where somebody's like, man, it'd be really cool if your game had rocket launchers in it. You're going to be like, I don't feel like adding that because now I got to add it to my player class. I have to add rocket launchers to my physics engine, to my inventory system, to my display, my rendering engine. I have to add it everywhere in my entire game. I have to add a new method every time I want to use that rocket launcher. I'm not going to do it. And we're not. That's exactly not what we're going to do. So instead, when we want to write a method that can take multiple different types, like a player can use just any game item, we're going to write a method that takes the super type. This use item method that takes game item. This method can be used with either weapons or health potions. So we have effectively the same thing on the previous slide. We have game item equals some weapon object or some health potion, but when the assignment is across a method call, that is where it's useful. You wouldn't do this within a single stack frame, but when you're communicating across stack frames, that's when you want to use polymorphism, because it helps you write just one method where you would need potentially hundreds of methods. We're just going to write one method that does everything. And we already saw this with this is why we used it for our BSTs. Our BST took a comparator of T, and that one method with the constructor at that point, and that one instance variable could work with any comparator that we write. So we could write, there could literally be thousands, tens of thousands of comparators out there that people write eventually. They can all use our BST. As long as they extend comparator, who cares? Who cares what type it actually is? Whatever T is and whatever the comparator is, as long as the comparator extends comparator of the type of that BST, who cares? One method does it all. You don't have to go and write a BST class for players, a BST class for health potions, a BST class for ints in decreasing order, a BST class for ints in absolute value order. You don't have to do that. You write one BST and leverage polymorphism to handle any comparator of any type between polymorphism and type parameters. Sort anything in any way. So this is the big selling point of polymorphism, is it makes classes so much simpler to write. Just one method. All right, milestone 1 done. T's done. All right, so that's polymorphism. That's why we use it. That's why it's powerful. So we do have that downside, but the selling point, the benefits strongly outweigh the downside. So in this method, we can only access anything known to the game item class, but that's fine. We'll live with that. And then We'll live with that downside to be able to simplify this method, to have this one method instead of hundreds of methods, one for each game item type that we have. Well worth the sacrifice. And in this case, we just want to call the use method. That use method is part of the game item class. And in practice, in the real world, the downside really is not a downside. It might seem restrictive, like, oh man, I'm stuck with only the same behavior of the game item class. That kind of sucks. But in reality, what you do is if you ever have a method using polymorphism like this, and you're like, man, I really want to call that get damage method, but I can't because it's in the weapon class. You don't just throw up your hands and give up like, oh crap, I guess I can't call that method. Sometimes you do because it just doesn't make sense to call the method. But if it makes sense to call the method, what we usually do is take that method from the game item class, from the weapon class, and just move it to the game item class. Just like we did in task 4, where we took a bunch of the functionality from the song class. We want movies to have all that functionality also, so we take all that functionality and move it into the rateable class. Now songs and movies both have that functionality, and we can use all that functionality in task 7. We can use all that functionality from either songs or movies because we'll have variables of type rateable. We can just access all of that rating behavior. That's why it's called rateable, because we can rate things. We can add ratings and get the average rating and the Bayesian average rating. We know all that things that anything that can be rated or rateable can have, which is songs and movies in our case. So downside really isn't a downside. You just got to reorganize your code sometimes to be able to get the functionality you want in the superclass. And if you have a method that takes a game item and it's trying to do weapon specific stuff, and like get damage is a bad example, because get damage really does belong in the game item, in the weapon class. It doesn't make sense for a potion to have a damage factor, unless you're using a negative damage for healing. Maybe you can make it make sense, but on the surface it doesn't really make sense. So you would just rethink the way you're using your code. If you have a generic game item method that's trying to access weapon specific behavior, you're probably doing something weird in your code, and you should rethink your approach, is usually what happens in practice. So in practice, we really don't run into the downside if your code's well structured, well organized. But we have another advantage. So that alone is a huge advantage. That alone is enough reason to use polymorphism, is to simplify your methods that can be coded to the superclasses. But we can go one step further. We can have one more benefit. So we have two major benefits for polymorphism. Is the polymorphism can be used as type parameters too. If I have an array list, say I want to build this inventory system. I have my pickup item that's going to take a game item. Cool, we just talked about that. But what do I do with that game item once I have it? Well, we can use polymorphism with our data structures too. So if I want an array list that stores both potions, health potions, and weapons, instead of having two array lists for my inventory, which would be painful, you have 100 different game item types, you have 100 different array lists for all of your inventory. It's going to be a pain to track like the total weight of all your inventory. You got to go loop through every single one of those array lists. That's painful. That sucks. No, we're just going to have one array list of type game item, and now whatever game item we come up with, we can store in this one array list, which is our total inventory of every game item that we have. So not only can we have variables or methods that take parameters of the super type and have it work for multiple different types, but we can have data structures of the super type and have a data structure store variables of different types, to store references to objects of different types. And this is where something we took for granted in Python. Python will just let you mix whatever types you want. You can put a double, an int, a string, a boolean, and a dictionary all in a single list. And Python's just like, yeah, whatever, because it's not strongly typed. It doesn't care. In Java, we got to do a lot of work just to get health potions and weapons in the same array list. But we finally did get there with polymorphism and embracing strong typing. But we do get there here. We have this array list with mixed types. Very nice, very handy to have. And this is where we get the full power of polymorphism. Methods that take supertypes in data structures coded to supertypes. And in this, there's certain things that just aren't really possible, or not really feasible at least, without polymorphism. So in the fall and spring semesters, our project is building a whole game engine and a game. And part of that game is a physics engine. And the physics engine, we have like, I want to say by the end of the semester, like 20 different game item types. Probably, maybe 15, I don't know, 15 to 20. And if we didn't embrace polymorphism, that physics engine would have to code up all 15 different types of game items inside of it. You'd have to go through all of the enemies, all the towers, all the players, all the projectiles, all the walls, go through every one of those in separate loops and do all of the physics engine stuff to them. But no, we don't do that. We have physics engine work with an array list of, it's actually game objects in that, of game objects, and then goes through all the game objects and just does physics stuff. And all the physics stuff is in the game object class, so the physics engine can work with all the physics stuff, just like game item has, in our example, has all the physical location of the object. It would have everything else it would need, its velocity as well, if we're building out the full example. And it has everything that the physics engine needs to be able to move that object. It's going to apply gravity, update velocity, update position, detect collisions. It takes the dimensions of each object and detects all the collisions. It can do all that without even knowing the type of each of the objects. And when we do create a new type in our game, the same physics engine just works with that new type. We don't have to go back to our physics engine and update it every single time we add a new type to our game. That'd be a pain in the ass. Nobody's going to do that. So we have our physics engine work to the base super type of every single object that can have physics applied to it in our game, and we write the physics engine one time only. One time, and it'll work for every single type that we come up with, as long as those types extend game object either directly or indirectly. Then our same physics engine just works. Physics is just magically applied to those new objects that we created because of the way that we embraced polymorphism. So this is the real power of polymorphism. We would never be able to get that game working. Any project of any real complexity, you wouldn't be able to get it working without embracing polymorphism. If you're using a strongly typed language, polymorphism pretty much a must, unless you're building just really small toy projects. Once you get anything of any substantial amount of code, polymorphism is pretty much required. We're doing on time, we're doing fine. Okay, and we have, so that's polymorphism, and we have a few cleanup topics. These are topics that really are related to inheritance, but they don't fit in the inheritance week, in the inheritance, I guess, lecture. It's only one lecture in the summer. It doesn't fit in the inheritance lecture because that lecture's already stuff. Like, I'm already scrambling just to get everything in that lecture. But with polymorphism, like I already talked about everything I need to with polymorphism. We're going to do a big old memory diagram and some live coding to reinforce everything we've seen. But we have a little extra time. We can talk about abstract classes, abstract methods, and interfaces. So let's do these cleanup topics right now. So methods can be abstract. This is an abstract method, which is a method that doesn't have a definition. I've declared the header for the method. So I said it's a method named use. It takes a reference to a player and it returns void. But I didn't say what it does. And I labeled that by giving it the keyword abstract and then capping it with a semicolon and just saying, here's a method. So I'm saying game item has a method named use that takes a player and returns void, but I don't know what it does. It just doesn't have a definition. So what happens when we call this method? Well, I don't know. It doesn't have a definition. And Java doesn't know either. Java doesn't know what should happen when this method is called. This method has a return type void, so the easy answer would be, well, it should just do nothing. But what happens if it has a return type of a player object? What should it return? Maybe null, I guess, maybe. But no, Java says if you have an abstract method, you just can't call it. You're not allowed to. You can't call an abstract method. It's a method that can't be called. Why the hell would you do that? So it's a method that it can't be called. It has no definition. And since the method can't be called, if your class has at least one abstract method in it, then the class itself has to be abstract. And if you have an abstract class, you cannot instantiate that class. So you cannot create objects of type GameItem, meaning you cannot say new GameItem if GameItem is abstract. Not allowed, because if you could have an object of type GameItem, you might be tempted to call the use method, and the use method isn't, you can't call it, you're not allowed to call it. So Java just says, just in case you might possibly call this method, we're not going to let you create the class at all. We're not going to let create the class, create objects of this type at all. So that's abstract classes. If you can have abstract methods. If you have any abstract methods in your class has to be abstract. For what it's worth, you can have a class be abstract. You can just add the keyword abstract to a class that has no abstract methods in it. And sometimes that's useful. Sometimes you just don't want people creating objects of your class type. You can make it abstract. I think somebody mentioned earlier in the semester the math class. Why not make the math class abstract if you don't want people instantiating it? And yeah, they absolutely could do that. They could make it abstract instead of making a private constructor. It would have effectively the same effect, as you can't create objects of that type. So why would you ever have abstract methods? Well, it's because they're intended to be, or abstract classes, it's because the class is intended to be inherited and extended, and then the class that extends the abstract class, that's the class that's going to implement the methods. So if I extend GameItem, the class that extends it, health potion and weapon, when we extend GameItem, we're going to be required to implement the use method. We have two options actually. We're either implementing the use method and giving it its definition for objects of that type, or we're going to be abstract. So like for a weapon, it might make sense for the weapon class to just be abstract, because what the hell's a weapon? Like I don't want a weapon in my game. I want swords, bow and arrows, rocket launchers, grenades. I want actual concrete, actual weapons. So weapon might actually be abstract as well. And then we have all the other classes that extend weapon, all of our different weapon types extending weapon itself. So it might make sense to have weapon be abstract. But we're either abstract or we implement all the abstract methods. But why? Again, why? Why are we doing all this? Why not just give all of your methods definitions? So we did this with our comparator class. Comparator class, we actually will go to our code from the inheritance lecture, and we'll refactor it. That's what we'll do in the live coding. We'll refactor those to make a little more sense. And that compare method really should have been abstract. Like that didn't make sense. What we did, we gave it a compare method that takes two values of type t and just returns false, because we didn't know about abstract methods at that point. So then in all of our classes that extend our comparator class, we have to just know to override the compare method. But if you make compare abstract, we're forcing you to implement the compare method. You don't have to. You can't make the mistake of implementing compare with the wrong types, like if we have ints instead of capital I integers, or if you just forget to override it at all. You can't make those mistakes if it's an abstract method, because you have an obligation to override that method. So why would you use abstract? It's when you want a method to be known to the superclass, but you have no meaningful default implementation for that method. return false wasn't a meaningful default implementation. We just had to give something there because we didn't know about abstract methods. But we want compare to be called from variables of type comparator. We want use to be able to be called through variables of type gameItem. So since we have that restriction with polymorphism, we can only call methods known to the superclass, to the variable type. If we have a variable of type gameItem and we want to call use on it, but we don't have any default implementation that makes sense, like a generic just item using an item. Back in inheritance lecture, we printed to the screen item used, and maybe there is some default behavior we want here. Maybe we want to do some inventory tracking or something like that. But if we don't have any meaningful default behavior, then we're just going to make it abstract to say, okay, you can call this method through variables of type gameItem, but it's up to the inheriting classes to decide what actually happens when that method is called. So that's why we use abstract classes. When we want a method to be known to the super type, but we have no meaningful default implementation. And we can take this a step further and go all the way to interfaces. So interfaces are classes, are like classes, they're interfaces. They're literally, it's the first thing we're seeing that's not a class. Our first code we can see that's not inside a class, but it's basically a class. It's still a container for state and behavior, but it is called an interface, not a class. So an interface has nothing but abstract methods. In fact, you don't even have to say abstract. This, by implication, is public and abstract, because that's all you can have in interfaces are public abstract methods. So we don't have to put public and abstract. We just put the method definition, not the definition, the declaration, and no definition because it's abstract, and that's our interface. So comparator really always should have been an interface, and we'll change the code, we'll refactor it today. An interface, because it has just one abstract method. Compare should be abstract, and that's the only thing in a comparator. Comparator should be an interface. So an interface is like a class, but has only abstract methods. Can't have any instance variables, for example. Can only have abstract methods. It's the only meaningful thing that it has. You can have, for what it's worth, you can have static variables and static methods in your interface, but abstract methods is the only thing that will be inherited at the object level, where static is at the class level. And then when you extend, or when you inherit from an interface, you use the keyword implements instead of extends. So a little bit of different syntax there. Then of course you have to override the already going to do that. It's going to say you didn't implement all the abstract methods, and you're going to be able to fix your mistake that way. All right, so why interfaces? Great question. Why interfaces? Well, in Java, you can only extend one class. And this is fairly Java specific. I think C++ also has C++ I think just lets you get in trouble. In true C++ fashion, you can do whatever you want, even if it'll break everything. Is this Java specific? It might be. I'm sure there are other languages. Anyway, in Java, for sure, you can only extend one class. So if you want to use multiple inheritance, you can't. You can't do extends gameItem and extends physics object. You can't do two extends. It's not allowed. Malware development course start. Nah. You want to write malware? Why do you want to write malware? And so you can only extend one class, but you can implement as many interfaces as you want. This implements, after implements, you have a comma-separated list of interfaces that you're implementing. You can implement hundreds of them. Who cares? You can implement as many as you want. Yeah, don't write malware. I don't want malware. I don't want malware in the world at all. Stop writing more. Nobody should teach you that. Nobody teach them that. So you can implement as many interfaces as you want. So that's why you would use interfaces. That's really the only reason. Otherwise, you would just use abstract classes. And we saw this very, very briefly, but when we were in the array list class, array list extend, does it extend anything? I don't know, but it implements a whole bunch of interfaces, which is usually useful. So now my int decreasing can be stored in variables of type comparator. We get that advantage that we had for polymorphism still, but we can implement as many as we want. So if we want our int decreasing to be a game item and a comparator of integers, that doesn't make sense in this context. But if we want to do that, we can, as long as comparator is an interface. Oops, got out of my slide. All right. Why do you want to write malware though? I mean, obviously there are people out there who do write malware, but why would you want to be one of them? What are you trying to take over? What are you trying to... Is it just to... I think it usually is just to make money, right? With malware. I feel like that's usually the end goal. There are more honorable ways to make money. So polymorphism, if an object is a type, it can be stored in variables of that type. Cool. I remind that we have interviews also in the fall and spring semester, so that's why I remind you of this so many times to make sure everybody knows it for the interviews. Oh, I did mention that earlier, didn't I? All right, so here's a bunch of code. Cool. Yeah. Let's do a memory diagram with it. So let's set this up in the memory diagram. Give me this one. Done with week 10. Done with week 6. Done with all the data. I can collapse all these. And week 11, memory diagram.txt. I got it all handy right here. Oh, hey, you get... I did this in office hours with someone. You get... I usually don't do that, but since I already flashed on the screen, there's a solution to one of the midterm problems. By the way, I won't give out electronic solutions. I accidentally did that one and kind of just embraced it. But if you come to office hours and ask, like, how did that midterm, how was that supposed to go? I'm always happy to do it in office hours. I just don't want electronic copies of everything floating around because, let's be honest, not all of you, most of you can, but not all of you can be trusted. They're gonna, solutions are gonna be shared everywhere, and it causes issues. And then next semester students start off with solutions, and the quizzes will be different each semester, sure, but it's... I don't want to get into it all, but it causes issues. All right, so here's the code. This is what we want to trace through, and I didn't talk about it in the slides because I just want to talk about it right here in this format. Let's resize things a little bit. Where's my face? Let me resize enough so I'm not blocking any code. That looks good. Sure. Okay. So let's go through this code, just kind of read the code first, and then we'll trace it, every single step. So let's talk about what we have here first, though. We have an interface usable, which defines the use method, similar to what we saw with game item in the slides, but we're making this a usable interface. So we're saying anything that can be used is going to implement the usable interface. Then we also have the game item abstract class, which has no abstract methods. That bugged me last time and I forgot to change it. But we have an abstract class with no abstract methods, which is allowed. That's fine, but doesn't really drive home the point. But we have one abstract method here. With our constructor for location, just one location. I did a lot of trimming down on this example so I can fit it on a slide, and I still can't fit all this code on a slide, but at least in the summer I can get it all on the screen at one time. But just one location, so we have a one-dimensional game instead of a two-dimensional game. It's fine. and a use method that takes a player, which has some default implementation. And then weapon and health potion, which is shortened to just potion here, both extend game item and implement the usable interface. So we can extend only one, at most one, or exactly one, because if we don't explicitly extend something, we extend object. We extend exactly one class, but we can implement as many interfaces as we want, and we could have a comma separated list and have more interfaces here. We only have one for this example because I'm struggling already to fit it all on the slide, on the screen. But this is the syntax. We extend one class, we implement as many interfaces as we want. And with this, the reason we would do a setup like this is sometimes we have things that are not game items that are also usable by the player. That's why you would split it up like this. So now I can have, maybe I want want a switch in my game that's part of the level. It's not a game item. It can't be stored in my player's inventory, but the player can still use that switch. So something like that would implement the usable interface without extending game item. So that'd be a reason to not put the use method in the game item class, but put it in a usable interface. So that's one of the practical reasons to do this. And then the rest we've seen potion and weapon code. We will trace through it, so we're going to go through every single line of it anyway, but we've talked about that stuff. And then the player class, we haven't seen the player class yet before, so we have HP and the damage that the player is going to deal, which is going to be set by the weapons that they equip. An inventory system, actually no, we saw player class in the slides, not exactly like this, but the pickup, we saw that in the slides. Use all items, we saw in the slides. I didn't mention it all, but it's going to go through the inventory and call use on every single item. We have to have a variable type usable because that's the type of our inventory. And then we can call the use method. That's the only thing we can do from a variable type usable, but that's the only thing we want to do from a variable type usable. If we have a bunch of usables, it's because we want to use them. Getters and setters. We're going to create a player, weapon, potion, pick them both up, and then the big one, use all items. The big thing is what happens when we call use on each object, which method gets called. Okay, so let's start tracing through this thing. Every trace ever has always started with the main method. I was surprised at how many students, it wasn't many, I want to say 3 or 4 that did this, but I was surprised it wasn't 0. The number of students who didn't have a main stack frame. Like, if you don't have a main stack frame, like, that's easy to grade, first of all. If you don't have a main stack frame, like, you have no fucking clue what you're doing. You probably didn't watch a single lecture. That was... and in every case, it wasn't, like, a simple mistake. It wasn't like, oh, obviously they just forgot to create the main stack frame. Like, they didn't even have the variables in there. So when I repeat things like that so many times in lecture, there is a reason. It's because no matter how many times I repeat something, there are still students who didn't hear me once. It's absolutely mind-boggling. I like writing about malware. Oh, that's way different. I thought when you said yes, I thought you were, because I asked, you want to write malware, and you said yes. So I'm also interested in offensive security. Oh yeah, those are good reasons. I like those reasons. Yeah, it's when you said yes that threw me off, because I'm like, you want to write malware? Yes, with 2 S's. Yeah, if you writing about and offensive security, those are good reasons. I still don't know anything about writing malware because I don't really have interest in it. So I'm still not really qualified to do it or interested in teaching it, but those are good reasons to learn it. I don't think there's any way to really teach a topic like that and not have, like, if I started a stream, I said, I'm going to teach you how to write malware so you can, write about it and do offensive security. There will be plenty of people in that stream who are there to be malicious. I don't think there's a good way. Like, all the cybersecurity content out there, a lot of it's being used by the other side, which is very unfortunate. So the player constructor doesn't have, there is no constructor here. So I get the default constructor, which just doesn't do anything, but HP was initialized inline. damage was initialized inline, and this returns. We've done tons of super constructor calls, and I would assume most anyone who attends lecture regularly doesn't have to do any more traces anyway, so this trace is probably mostly useless. We're still going to go through it so I can make my big points that I want to make when we get to use all items. But these first constructor calls, you've all been through this 100 times. Weapon. So I'll talk about cybersecurity during it. Why not? Except I don't know what else I want to say about that. But yeah, I could anything. I even get a little worried when I'm talking about damage. When I'm talking about preventing things, preventing against security concerns in certain classes, because talking about the prevention by necessity, I have to talk about the attack as well. So I basically have to teach you how to launch the attack, to teach you how to prevent the attack. So it does get a little awkward sometimes, because I do worry like somebody's going to take that knowledge and go be malicious about it with it. So the weapon gets those two variables, and then game item just gets location. So how do we teach prevention in a way that doesn't also teach you how to launch the attacks themselves? It's kind of a weird thing. Location negative 0.5, right? And this is how, again, this is gonna fall on preaching to the choir here, but when I'm going through a trace, like I don't just go, oh yeah, I know what my code does, I'm just gonna code it all up. I go line by line and just double check absolutely everything and go pretty blindly through the traces, because I'm not going to make mistakes that way. I saw for the midterm a lot of just shortcuts and people who are clearly using the clone button here. Not too many people, but a few people clearly used the clone button and had obvious mistakes that they wouldn't have made if they didn't use the clone button. Just little things like that. Just go step by step and actually do the damn trace. Some people have to take the final exam because they wanted to spend a few fewer minutes taking the midterm, and now they have to waste hours of their life and a lot of extra stress over the next week, worrying about whether they're going to fail the class or not, because they wanted to save 1 minute not actually typing everything out during the midterm. It's a choice they made. It's unfortunate, but they didn't have enough information to be able to determine if they actually knew what they were doing or if they were just guessing. Just go through step by step and do all the work. It's not that hard. New stack frame. I didn't label this. It can be hard. Let me rephrase it. It can be hard when you're first learning it, like you are. But there's one in particular I'm thinking of during grading that I think they probably knew what they were doing, but they took so many shortcuts that I couldn't actually determine if they did or not, or if they were just guessing. Potion doesn't have any instance variables, so it's just location. We have our super constructor call. Oh, so much code. Super constructor call, which is explicit. I made sure it was explicit on all both the OOP quizzes too. But still, good number of students missed it. Uh, 3.5. 3.5. Return. Oh, it's 300. Pickup. So our first method that uses, I can actually get some commentary here. First method that actually uses some polymorphism, we're calling pickup from player dot pickup. So from OX100. But overall, just to get back into positivity, overall the midterm I think went really well. The majority of the class did quite well on them. Item, weapon. Weapon is OX200. Except code blocks. Like, almost all of you forgot your code blocks. Or, I don't know, forgot or... that happens every semester. I think I just got to spend more time on code blocks. I'm thinking of adding, for next semester, adding another quiz that's just like the basics. I'm hesitant to do that because you should know all the basics from 115, but code blocks is the one thing that we don't do in 115 that we teach at the beginning of 116 just very briefly because I still see it as a 115 topic even though you didn't have to do it in your traces. Code blocks is still a 115 topic even if you didn't have to trace them. But I don't know. I don't know if I want to have a whole quiz just for code blocks. Pick up, but maybe I'll just label it the 115 like a pre-quiz or review quiz. And if you fail that when I say go back to 115, you gotta go study again. Aside from code blocks, if you fail anything other than the code blocks, pick up player. So this is an object of type player. So player pickup took an item, and we're doing this dot inventory dot add this dot oopsie, went too fast. I missed a whole instance variable here. So we have inventory set to a new array list with nothing in it, and we got OX400. All right, so this dot inventory dot add, we're adding to this array list here the value item. We go back to the stack frame item OX200. So we're going to add at index 0 OX200. This returns. We call pickup again. And I am cheesing this one a little bit, going through all the stuff that we already know about. Missing a few things there. Hopefully I got no other mistakes on here. 100. I usually go through every single step in lectures, and if I were ever doing one of these for credit, I'm going to go through absolutely every single step. Make sure I have no mistakes in there. Double check things and whatnot. Potion is OX300. That's wrong. OX300. Item. Oh goodness. This dot inventory dot add item 1 OX300, and this returns. Okay, now we get to the interesting. Oops, I gotta stop scrolling. Use all items. So we get a stack frame use all items called from the player, which is OX100. So this OX100. Now we're ready for the big one. Hey, how you doing, Tobias? I'm doing all right. So use all items from the player class. We're right here, and we have a code block. What most of y'all forgot. And if that wasn't clear, I chalked that one up to, like, I gotta structure the course a little differently. If the majority of you are making a mistake, that's my mistake. If a few of you make a mistake, that's your mistake. Since the majority of you don't have your code blocks, I gotta change something in lecture or the way we're assessing things. Maybe just make code blocks a learning objective and say, look, you gotta do your code blocks right. Because I think what it is, my speculation, is that you're focused on data structures in OOP because I puff those up as these are the things. OOP is superconstructor calls and which method is called, and data structures is navigating these node-based data structures using recursion. Like, those are the things that I'm assessing on the midterm. Those are the things I build up, and those are the things that we focus on in the memory diagrams in lecture. and I just don't reinforce code blocks much, and I don't make it sound important. Just at the beginning of the semester, I'm like, these are code blocks, ain't that neat? And then they pop up like once or twice after that. So when you go into the midterm and you're thinking, okay, node-based data structures, superclass constructors, I can't forget my superclass constructors. Just said that 100 times in lecture. I'm not forgetting my superclass constructors. And that's all the stuff that's going through your mind. You're not thinking about hitting the code block button. So I think that's what's going on. It's just something that's easy to put on the back burner and forget about. The way it's presented in class and the way we assess in this class. But this is in a code block. Since I have a code block here, and specifically with for loops, the iteration variable is part of the code block for that for loop. And it's important that we trace our code blocks because at the end of the code block, any variables that were declared in that code block are removed from memory. This actually isn't the case in Python. That's why you don't talk about code blocks in your memory diagrams in Python. But in Java, once you hit the closing brace, all variables that are part of that code block are removed from memory. I think I got to set up examples where that's relevant. The problem is if you make any code where that's relevant would not compile. Coming up with an example that compiles that also cares about code blocks is tough. Maybe I should just stop caring about code blocks. It's because of that, because it just wouldn't compile. So item.use. Item.use. This is where we finally get to our polymorphism stuff. Any OOP trace like this, there's just so much setup. We just had to do all of that just to get to this point where I can talk about this. Item.use. We're calling the use method from this object right here. So let's get what we know. We have use where this is OX200. We know that much. But which use method is called? We have an abstract use method here, we have a use method here, we have a use method here. Which one is called? Where's my potion class? Potion class is so small I can't even see it. And no use method in the potion class. So which one is called? Well, and the way this is set up, it's hard to even make a mistake on this one. Because if you look at the variable type, you might be tempted to look at the variable type. And if you're just reading the code, if you're not doing a memory diagram, the memory diagram makes it more clear. But if you're just reading the code, you see usable, you're going to be tempted to go to the usable interface. Well, use is abstract there, and then you say, this code doesn't compile, this is a trick question, and then submit that. Some students do that. I haven't seen that in a long time, but you can't call that from usable anyway, so it's hard to make a mistake here. But if this were a game item, we would go to the game item class, find this use method, and we'd be tempted to call this one because that matches the, I keep losing where I am, because that matches the variable type. The variable is type usable, so it's a reasonable thing to think, well, let's go to the variable type. That is not how polymorphism works. It's always, which method is called always depends on the type of the object calling the method. So OX200 is the calling object. It's of type weapon. So just like we've done for every memory diagram, I've always done it this way because I want to build up to this one. I want to make sure this one's clear. This is an object of type weapon. So we go to the weapon class to look for the method that's being called. So we've always done, nothing's changed. I have never gone to the code and said, oh, this is a weapon, this is a usable, let's go to the usable class. I've never done that. Always the object on the heap, go to the type for that object, and then find the method we're looking for, which is right here. So this is the use method that's being called. Always depends on the type of the object on the heap, not the variable type. Okay, so this is the method that's being called. and we have use, oops, I don't have my parameter here. So we have a parameter player, and use was called with this from the use all items stack frame. This was OX100. So OX100. And then we have player dot set damage. So we're calling set damage from the player. It's another common thing for getting getters and setters. That was much less common. So I'm blaming students on that one. Individuals did poorly on that one. Joking, semi-joking there, obviously. This is OX100. Because I mean, in every trace we do a lot of getter and setter calls. Set damage with this dot damage from the use stack frame. Use this is 200 dot damage 15. So 15, and set damage was from a player. So I'm looking in the player class for set damage. Set damage, the parameter is damage, and this dot damage equals damage, traditional setter. So this dot damage equals damage. So we just equipped this weapon and increased our damage output to 15 is effectively what happened there. That's the end of set damage. That's the end of use. And we're back in use all items. So use all items, we got to the end of the loop. So we're going to the next inventory item, OX300. And we're calling use again, item.use. So item.use, we're calling use from this object right here. So we have use. This is OX300. OX300 is of type potion. So we go to the potion class. We look for a method called use that takes a player. We do not find it. Oh, I forgot a few things to mention. We do not find it, so we continue our search to the superclass. This, again, works the same way it always has. We're going to the superclass. We do not go to the interface. If we go to an interface, we're only going to find abstract methods anyway. So we're going to go to the superclass that we extend, the single superclass, and continue our search there. So, oops, wrong class. We're going to go to game item, look for use method, we find it, and this is the use method that we get, this one right here. So we have use, it takes player, which is this, OX100, this from the use all items stack frame. And we're going to call this method right here. One thing I forgot to mention, there are no superclass constructor calls for interfaces because interfaces can't have constructors. They don't even have the default constructor. There's no constructor at all for interfaces, so nothing to trace. And if I were to give you a trace that has an interface, I'm not going to because of, I already explained that. But if you were ever in a situation in your life where you're tracing code with interfaces, the trick to it is to completely ignore the interface. Just completely ignore this, completely ignore this, just pretend it doesn't even exist. Because it has no effect on your trace at all. Interfaces have no effect on the execution of your code whatsoever. Interfaces only have an effect on whether or not your code compiles. So, and the same with the variable types, like putting this potion in a usable, like that's the types here are only going to determine if your code compiles, if all the method calls are allowed, and that's all at compile time. So all of strong typing, in fact, is all compile time, checked at compile time. Once your code runs, the types don't really do anything. The types don't have any effect on your code. The variable types don't have any effect on your code. Any of these types don't change the way your code runs. The object types do. The actual objects you have in memory do, but not the variable types in the code. They just don't change how your code runs. It's all compile time checks. So that's like a tip for your traces. It's why we don't put any types except the object types. Those are the only ones that matter. Those are the only ones we put in our trace. We don't put any variable types for any of these variables in our code. We don't put the type parameters of our array list. We don't put any of that stuff on there because that's all compile time stuff. The only one that matters, types of the objects on the heap. So that's all we trace. Only types that we talk about in our traces. All right, so we have this right here, player dot set HP of player dot get HP plus 20. I have to resolve what's inside the parentheses first. So get HP is going on the stack first. Get HP, both capital. This is OX100. Get HP from the player class is going to return HP. I would prefer this dot. I missed the this dot. This dot HP 50, so that's going to return 50 plus 20, so 70. Player dot set HP, and if this were a trace, I would split this into multiple lines with intermediate variables, just so your trace is more clear. The way I have this set up, I have to just remember a bunch of stuff going from frame to frame. I have to remember that this resolved to 50, and then I added 20. I would store this in an intermediate variable if it were on your quiz, just to make it easier for you and lighten the cognitive load that you have. But I didn't do that for myself. So set HP, HP. So I have to remember, okay, this was 70. And for not partial credit, but for another reason I do that is if this is wrong on your quiz, I don't know where you made a mistake, which means I don't know if it was a simple mistake that I don't care about or if it was a major mistake that is fundamentally related to the learning objectives of the course. If this is wrong, I just don't know, and if I don't know, it has to be a fail on the quiz. So if I have intermediate variables like that, there were quite a few cases for midterm grading where there were mistakes all over the place on the trace, but there was enough information in there. I could look at the intermediate variables and figure out what went wrong. And sometimes it was a few mathematical errors that caused you to have the wrong values in certain places or the wrong output. You could have the wrong output and still pass a quiz, as long as I could tell that it was very clear where you made the mistake. And if that mistake wasn't related to what I was assessing, it's fine. For example, I had a few students who read greater than as less than and took the min instead of the max for the linked list question. It's fine, whatever. There was enough information there that I could tell that they traversed the linked list properly, but just read their greater than and less than the wrong way. Like, I don't care. Like, that's obviously a simple mistake. And what I was assessing is, can you traverse a linked list using recursion? That's what I wanted to see. And that's what I saw. So it's fine. Sorry, midterm grading's on my mind after spending so many hours doing that. So set HP. This dot HP equals HP. So this gets set to 70. Cross this out. That's the end of our use method. So we get all the way back to use all items. These crossed out stack frames are literally deleted. They're removed from memory. So I go back to the next uncrossed out stack frame. That's use all items. I was iterating over the inventory. I got to the end of the loop, and I've already iterated through both values. So this code block is gone. I get to the end of the stack frame. That returns back to the main stack frame. And we're at the end of the main stack frame. That's the end of the program. And that's our trace. I want to just make sure I don't think I'm forgetting anything. Yeah. Just want to make sure I didn't have anything at the end of those slides. means I'm actually making good time. All right. Polymorphism example, that should be plural, but I guess it's all one big example. Let me just example did I do? Let me reuse this package. Grab my starting point here. Okay. Oh, I might take a nap between lectures today. Goodness. All right. I kind of want to start in comparator because I don't know. I just feel like starting in comparator. So let's take this code. This code is where we were at the end of the inheritance lecture, and I want to refactor this code using polymorphism. So let's take what we've learned about polymorphism and refactor this code. And the first big one that I don't like doing the comparator during inheritance week because this really should be an interface the whole time. And it bugs me that we create it as a class first, that we pretty much have to do. But this return false and everything, let's fix this. This is the first thing I want to do because I'm eager to get rid of this issue. So let's turn comparator into an interface. This is what it always should have been. And when we create an interface, the methods are automatically public and static. So if I do, let's get rid of this. So if I do public static here, public abstract. Public and abstract. So if I put public and abstract, the IntelliJ is actually going to grade these out for me. And it's going to say this is redundant because it has to be public. Same with abstract. Redundant for interface methods because it has to be abstract. So even though I don't have public and abstract keywords here, this is still public and abstract. And we can take this a step, not a step further, but if I have like int x equals 7 here, it'll let me put a variable here, and this looks like an instance variable. And I can try to add my private, but that's going to give me an error. Private not allowed here. So I can create what kind of looks like an instance variable, but it isn't. You can't have instance variables in interfaces. It's not allowed. The only thing you can have is abstract methods. So what's up with this int x equals 7? Why am I not getting errors here? It's kind of weird. Well, it's because it's public. That's going to be grayed out just like it was for the method because it has to be public. But it also has to be, if I could spell, it also has to be static, and it also has to be final. So we can create variables, but they are implied to be public, static, and final. So we can have constants in our comparators, constants that belong to the comparator interface itself, but we can't have, we can have static methods too, by the way, but we can't have instance variables. So we can have a static methods and static variables for days. Because they belong to the interface itself, we can't have any issues with that. So comparator dot x, we can access this through the comparator itself. And that's fine, but it's not an instance variable. It doesn't belong to objects of any type. So you can, if you type int x equals 7 and you create variables here, don't say, oh, Jesse told me you can't have anything else in interfaces. So I guess to be accurate, the only non-static things you can have in interfaces are abstract methods. And there's even an asterisk on that. You can use the default keyword. I always forget the syntax for this, but So you can actually give implementations to your methods if you use the default keyword, but I'm already off track a bit as it is. So we're going to change our comparator to an interface like this. It just has an abstract method compare. And when we get to our implementations here, we're going to get errors over here. Because comparator is an interface now, we can't use the keyword extends. We have to use implements. So for all of our comparators, implements. We implement comparators. We extend classes. Then insertion sort, all this works just the same. We have our insertion sort constructor, which takes a comparator of t, our instance variable comparator of t, and then when I create my insertion sort, I'm specifying that t is integer, then giving it an int decreasing. Int decreasing implements the comparator interface, so it is a comparator of integers. Everything matches. Int decreasing is a comparator of integer. It is a comparator of integer, so the method call is fine. The assignment here to the instance variable is fine, and I will get this code running just fine, and we get our ints sorted in decreasing order just like we did before. So that's our comparator. So we fixed that, got rid of that issue, and now we don't have, like last time we had int, and then we relied on our annotation to catch that error. Well, now the interface is going to catch that error too. It's going to say you have an abstract method that you have not implemented. Your choices are implement the thing or make yourself abstract. But if we make ourselves abstract, we're going to break this code here because now we're trying to create an object of an abstract type. We can't do that. So we're just going to do this properly. Okay. Now let's get our other stuff refactored. Game item. Let's just make it abstract right away because that's what we're going to do. Actually, no, let's do it the other way to just show what happens. Is a game item should have all the location stuff. So game item has X location, Y location, constructor to initialize those variables, a method to move an object, getters for X and Y, that's fine, toString that prints X and Y to the screen, that's fine. But when we get to the use methods, these are the ones that didn't make sense. It didn't make sense to just have print item use. We want each inheriting type to define what happens when it's used. So when you use a health potion, when you use a weapon, those classes should determine what actually happens. So we don't have any meaningful default behavior for this use method. It's fine. Yeah, that's fine. For this use method, so we're going to make that method abstract, and we're going to do the same thing with this method that takes a player, the use method that takes a player. I'm going to make this abstract. Because I don't have any meaningful default implementation. They return void, so the default implementation can just be do nothing like the second one was. But makes more sense to me to make them abstract, because now that forces anyone who extends game item, it's going to say, hey, you have these two use methods you have to implement. Tell me what happens when you're used, so you don't get the default behavior of just nothing happening. Because then you might get the default behavior of nothing when you did want to override it, or you overrode it but you misspelled use and you don't like your override annotations. There's more fail-safes we can have. But we have issues here. We have errors because these methods are abstract. Now we have a concrete. Concrete is the opposite of abstract, by the way. If your class isn't abstract, it's concrete. So this is a concrete class with abstract methods in it. That's not allowed, so we have to make our class itself abstract. Now the errors down here went away because now we have an abstract class with abstract methods. That's perfectly fine. Now we get errors elsewhere. We implemented both methods here in the weapon class, so that's fine. Cool. But health potion, not so much. Oh, I want to rewrite this line too. Every time I see that, I'm reminded of how frustrating it is. Taking negative damage. I know I mentioned it earlier this lecture, but I don't. Taking negative damage for a potion. I blame Paul for that one. So let's rewrite this. In the slides, I changed it, but I forgot to change it here. So set HP, but player doesn't have HP in this example. Oh, no, it does. Get HP, but not set HP. So let's add a setter. Let's fix this. IntelliJ, stop collapsing all of my methods. So let's do public void set HP int HP, right, just the way it was in the slides. This dot HP equals HP. All right, set HP player dot get HP plus increase math dot min of player dot get max HP. Something I wouldn't do on a trace just because there's so many getter and setter calls here. You have 1, 2, 3. I guess it's only 3, but 3 method calls for this one method call. So I guess 4 total. Would be a little bit of a pain to trace. But this is going to make sure that we don't overheal players. We're going to limit them to their max HP like we did earlier in the course. So we have the use method that takes a player, and we have this implemented much better now instead of just taking negative damage. And we're getting errors here because we have an abstract method that we have not implemented. The use method, just the straight up use method that, and this is an override. The straight up use method that doesn't take any parameters. So let's override that. Public void use doesn't take any parameters, and we'll still just simulate this. Use the health potion, yay! And now everything should be fine. Move H. Have oh, not player though, because sometimes for some reason we have player extending game item. Okay, everything should run. Cool. So we changed game item to be an abstract class with some abstract methods. And health potion and weapon, since they extend game item, they have the obligation to implement all the abstract methods, or else we're going to get an error. So weapon and health potion both implement both of those use methods. The overloaded use method, you can have multiple methods of the same name as long as they take different parameter lists. We've seen that a few times this semester already. So I don't think I have to go into that. And actually, I just did it anyway. And everything runs, everything compiles, and we successfully refactored all of our inheritance lecture content to take advantage of polymorphism. And I'm mostly talking to myself here, but does anyone have any questions? I guess I could have questions. If you have questions, because that's really everything that I had to cover in this lecture, and we have, I mean, there's almost an extra hour. I'm tempted to just end stream early. I guess I'll go over task 7 in the meantime, and if there are no questions after I go through what asked of task 7 and drop a few hints and stuff, then I'm going to just shut down stream. If nobody's interested in lecture, why should I be? I know why I should be, because for the recording, because not everybody watches live, but they watch later, is the actual answer there. But if I'm out of content and there are no questions, I'm not just going to ramble for an hour. Actually, I could ramble for an hour. Maybe I will just ramble for an hour. I like talking. But let's go through task 7, then see how I feel at the end. Because you already have everything that you need for task 7. The big thing is having an instance variable in the media library class that's going to store both songs and movies. That was the big thing that I mentioned at the top of the lecture. That was the big thing we needed for task 7. So you're creating this media library class, which is going to have this populate library method, which is going to call all 3 of the methods from your task 6 to get all of the data from from 3 different files into your media library. This is just on the other side of task 6. You're calling your methods. Methods already exist. They're tested. Autolab said they're good. You're all good with that. You call all 3 of those methods to get all that inside your media library class, your object. So when you call populate library, you're going to end up at the end with an array list of movies and an array list of songs. You have those 2 things. And you want to combine those into a single array list, which you can do with polymorphism, because you're going to create one array list of ratables as an instance variable, and then put all of your movies and songs inside that one single array list. And the rest of the assignment is writing this top k ratables, which is going to give you the top k ratables in order of their Bayesian average rating, with 2 extra ratings of 3. So the same setup as your Bayesian rating comparator. And it's up to you how you want to sort. Any way you want to sort. You can use your BST. You can use a custom sorting method. You can use our insertion sort method that we saw in lecture. You can grab that code and use your comparator. You can write your own Java style comparator and use Java's sorting methods. However you want to sort. I mean, at this point, 2 semesters into your program career, you've seen a multitude of ways to sort a data structure. So however you can sort, do it. If you're sorting using the comparator, the Bayesian average comparator, that was written for songs specifically, so you'd want to write another comparator, just copy and paste that, and replace song with ratable. So now you can compare ratables with it. And then return those ratables in an array list. So if you're using your BST, we do need to convert that linked list into an array list. So you would have one extra step there. But this is the crux of it. And then if k, so for example, if k is 10, you're creating a top 10 list. If k is 2, give me the top 2. And in order, so what's at index 0 should be the highest rated ratable, either song or movie, in your data structure. And that's it. It's really 2 methods. Populate library, which is just using your code from before. But what to do with all that data is the new thing, is putting it in a single data structure. And top k ratables is the bulk of it, but honestly it's sorting. We've sorted so many times. I sorted 2 different times with full examples in lecture with the insertion sort and BSTs. You know how to sort. You know how to sort by now for sure. You've seen how to sort. I guess I haven't asked you to just go off and sort before, so I guess it's a little new. It's good practice. Yeah, don't test with any 2 songs or movies with the same exact Bayesian average rating. That'd be a pain. So we're not going to do it. It simplifies your tests, simplifies my tests, just makes things a lot easier. With this clause, if I remove this clause, the assignment gets a significant amount more tedious without you actually learning more, at least not learning more about the learning objectives of CSE116. You would learn more, but it'd be an exercise in tedium, which would get you, just general programming experience, I guess. Maybe there would be some value in that, but not enough. And then you're testing. So compare rateable arrays. This testing utility method, I have to warn you, I think I have it right here. This is significantly simpler than what you've done on task 6. So don't overthink the testing utility. This one is very straightforward. You just go through index by index and check the titles. It's much, much easier than what you just did for task 6. I say what you just did, but I haven't checked the stats yet. It might be what you're still doing for a lot of you. I don't know. I checked yesterday and it was looking pretty bad, but a lot of you have been pulling through at the last minute on these expected deadlines. Which last minute, you only have 48 hours total, so last minute isn't even that late. As strange as it is to say. And then testing, call populate library, call top K ratables, and then make sure you get the right top K ratables. You can use your files. You can use file testing like we did for task 6. Nope, that's the end of that sentence. Yeah, use your files, like set up files the same way in the data directory. So when you call populate library, give it 3 file names for files that are in your data directory, and then call top K ratables. You should work it out by hand. Make sure you know what the top K ratables that you're expecting, what they are, and then code that up as your test case and make sure that that's actually what was returned. I think testing for this one, aside from setting up the files, but you already did that in task 6, you should already have test files set up. Do the math to figure out what the top K ratables are. I think this testing is more straightforward than most other assignments. Actually, I think overall task 7 is pretty straightforward compared to what you've done in tasks 3, 4, 5, and 6. I think task 7 is a little dipped down in difficulty. And then task 8 will be... task 8 is a little harder again, but I also hold your hand through lecture, pretty tightly. I really walk you through task 8 very closely. All right. And I haven't seen a question and all that. If y'all don't care to show up to lecture and ask questions, I'm out. But yeah, I do decrease the time estimate too to indicate that. Yeah, I'm just gonna end stream here. If there are no questions, I said everything I want to say. There are definitely things that could be covered, but if I'm not just gonna cover them unprompted. If nobody wants to hear them, I'm not gonna do it. All right, take care, me or anybody watching the video. All right, see ya.